right, now let's talk a little bit about this concept of entomotoxicology. So think about those words. Entomo means entomology. Toxicology, that is the study of toxins or study of chemicals in a body and how they react with that body. So this is one of those more modern aspects of study when it comes to forensic entomology. We're starting seeing a lot of toxicologists, a lot of general forensic scientists start to really understand what is going on with this. So the idea of entomotoxicology follows the idea of you are what you eat. Since insects are feeding on a body after death, or parasites are feeding on living humans and animals, whatever chemicals happen to be in that animal or in that human's body are going to be taken in by the insects. Now, over the past few decades, there have been an apparent increase in the incidence of drug-related deaths. So we're starting to see more and more people overdosing on these different drugs. They're found later. They're found in their houses, something like that. And the decedents in such cases may not be discovered for a substantial period of time. So think about having to be a toxicologist in this case. When you are testing for drugs or alcohol or something in the system, that is going to rely upon having some intact tissue, some intact fluids in the environment, maybe intact stomach contents, something. Once you get to that decomposition stage, everything has just gone all wonky and everything's going to be out of whack. Once you get to fully skeletonized, there's really nothing left. There are certain drugs that will embed themselves in the bones, in the teeth, whatever, but they're not going to all do that, and they may not be in such a state that we can actually find them. So people have started looking at the insects that are then feeding on the body. So the accuracy of analyzing insects and deaths involving, say, narcotic intoxication has been subject to debate in recent years. So people have started to think, okay, we've got maggots feeding on the body. There's nothing we can test on the body. What happens if we test the maggots? Now, there's only a few studies available that have explored the effects of drugs contained in decomposing tissues on things like fly colonization or on ovipositional behavior, or on the rates of development of carrion-frequenting insects feeding on such resources. So there's this idea of, all right, this is a drug. So if these maggots are feeding on this body, what does that mean for the development of these maggots? And then can we use these maggots then to test for this drug? So that's sort of where things are going on. We have noticed a lot of effects of these different drugs on maggots. So there are certain drugs that make maggots grow quickly. There are certain drugs that retard their growth. There are certain drugs that make them grow in strange ways. I actually have a student right now who is looking at some over-the-counter substances, things like cough syrup and caffeine, and seeing how they affect maggots. And spoiler alert, one of the things that she found was that caffeine at lethal doses for humans will kill maggots. So because you can buy caffeine in pill form and you can buy it in powder form, we are getting more and more deaths from caffeine overdose, which is just crazy. But the maggots that are then feeding on that same level of caffeine will also die. So that's an interesting new development, right? You get these people who die of caffeine overdose, maybe maggots won't be able to actually live on their body. That's weird, and that's upsetting. So there's all manner of things like that going on. How are these drugs that are present on a body actually going to affect how these maggots grow? And then what can we do with that information? So there's not a lot of studies on it. There's also relatively few studies that have examined the effects of other tissue contaminants, things like toxins or environmental pollutants or antibiotics, on these behaviors or the developmental patterns of insects colonizing these tissues. One interesting thing I might have told you earlier in the semester is people who die when they're in the midst of chemotherapy. They are not really attractive to flies. So I have seen at the body farm these bodies that have died in the middle of cancer treatments. They don't have a lot of bacteria in their body. They're on a lot of antibiotics. They're really knocking down their immune system, all that. They will just mummify. Maggots will not be attracted to them. All around them, there can be all these bodies. There's plenty of room for them. They're perfectly available for these flies to show up, but the maggots don't show up because there's a lot of mediation of when these insects are going to show up on the body when based on the bacteria. So if that changes, then this succession can change and the rate of growth and feeding can change. And so that becomes a problem. Now, most of the recent interest in entomotoxicology is the potential to use these carrion-frequenting insects as an alternative to toxicological specimens. So in situations where traditional toxicological sources like blood or urine or solid tissues, they're not available for analysis for some reason, you can use the maggots to test for drugs. So the use of maggots for this purpose is actually pretty well documented. People have been using these for a while, and they've been used to assess both the cause and manner of death in various situations. It has even been extended to analyzing insect remnants encountered with mummified or skeletonized remains. So think back to the beetles, right? The dermestid beetles, you've got that frass that they produce. If there was anything in the body that the beetle could not metabolize, it is going to poop it out in that frass. You can test that frass for toxicology. There was a relatively recent case where a guy wandered out into the woods in the middle of winter, way up north. He died of exposure, they think, but they didn't find him. So he's reported missing in November. They found him when the snow thawed around May that next year. So he was basically fully skeletonized, but he had gone out there and died at a time when maggots were still able to get to him. So they hadn't gone dormant yet. They'd gone through their full developmental stage. Their pupal casings were left behind. They were actually able to pull drugs from the pupal casings that were left behind around that skeleton. So they could tell that there were drugs in the system, and that helped explain why this guy wandered into the woods in the middle of a cold night wearing just shorts and a t-shirt. So that sort of thing can happen. You just need to work on the methods of pulling the drugs out of these maggots or out of whatever insect parts you have, and knowing that it's possible, which is why I'm telling you about it today. So drugs or toxins are ingested by carrion-feeding insects, and they are dealt with a little bit differently than they are in the human. They are concentrated throughout the insect tissue. So instead of being able to metabolize these drugs, most of the insects can't get rid of them. They don't have a liver the same way that we do to break them down. They don't react the same way that they do in our human body. Instead, the insects are going to sequester these chemicals in some way. They're going to try to get rid of them or neutralize them in a slightly different way than we would. So they tend to be concentrated throughout the tissue. This includes the cuticle of the insect, any of the cast larval skins or the exuvia, the pupal casings, and the fecal material. So all of these things are available for analysis if you find them at the scene. Now, in general, the arthropods or the arthropod parts are homogenized or processed in the same way that other tissues are for toxicological analysis. So if you end up working in a toxicology lab, when you take these samples, you're going to grab a sample, you're going to homogenize it, so blend it all together so it's all there. You add your buffers and whatever else you need to add, and then run it through your machines and run it through your testing protocols. You can do the exact same thing with insects. So you just homogenize it and then run it through your normal protocols. In the case of things like pupal casings or exuvia or exoskeletons, you may need a more vigorous extraction technique. So use something that was originally developed for hair and nails. That's because it has that same sort of protection, that keratinization like we have in hair and nails. So you need a little bit more to extract stuff. So you can ensure adequate extraction of these chemicals by using those techniques. Now, once the tissues are prepped, they are analyzed using a variety of methods. You can use radioimmunoassay, you can use gas chromatography, GC mass spec, so gas chromatography, mass spectrometry, thin layer chromatography, basically all those neat techniques that you've learned in your microbiology, your chemistry courses, all those things in order to analyze different chemicals. What is this thing? Well, you can do that exact same thing with these insect parts and figure out what drugs are there. So, radioimmunoassay, this is the use of radioactively labeled antibodies. These antibodies are used to measure the amount of some substance in the tissue. So what happens here is the antibodies will specifically bind with whatever substance we want to know about. So we've designed these antibodies. Remember, antibodies are just a simple immune system reaction to a particular substance. So basically we take animals, we put this substance in them, they create these antibodies to bind to it, now we have antibodies. So these antibodies are added to a liquid formulation of the tissue with an unknown concentration of our substance of interest. So we take these known antibodies, we homogenize the tissue, we throw in the antibodies into that mix, and then the number of antibodies that bind to that substance and the number that don't can then be read with a Geiger counter. So it's basically we're using this whole radiation idea, right, in order to label this substance. So we just see what binds and then what then shows up on that Geiger counter. This gives us the ability to infer how much substance of this particular unknown or this particular chemical is in a tissue sample. So this is actually one of the least expensive methods used, but it is really, really labor intensive, and you kind of have to work with radioactive things. So it does take special training and certification because of those radioactive materials. But it is inexpensive, and it is still used in a lot of labs today because it can be done pretty quickly once you have the materials. You just basically mash things up, add some of these antibodies, read it with a Geiger counter. A little more expensive is thin layer chromatography. So you have probably run something like this in any chemistry class or, workshop that you've done, or if you're just bored at home, whatever. This is where you put in, you have a liquid substance, you can take a piece of paper, run some pen on it, put it in that liquid, and the liquid's going to be drawn up along that column or along that paper, and it's going to separate out the different parts of that chemical. Yeah, same idea, except a little bit more in depth for a lab situation. So thin layer chromatography is commonly known as TLC. It's a technique used to separate mixture. So it's especially important when you have a mix of something or other. Now it's performed on a sheet of glass or a sheet of plastic or a sheet of aluminum foil, something like that, instead of paper usually. But it is coated with a thin layer of absorbent material, usually silica gel or aluminum oxide or cellulose, hence the name thin layer chromatography. So it's a solid with a thin layer of some sort of absorbent material. Now, let's say we have an unknown sample. That unknown sample is then applied to the base of that plate, the base of that solid substance. So down here somewhere. So you would just apply it there, either in a dot or a line. And then that bottom edge of this plate is submerged in a solvent of some sort. So, water is the universal solvent, but you can also use all manner of different things. And this just depends on the protocol for the different chemicals. So anytime you've done this in a lab, you've had some sort of, probably a glass plate with some sort of silica on it. You've dotted something at the bottom here and you've put it in a beaker with some sort of chemical and it's drawn its way up. And you probably had to do that rate of transfer. There's a little bit of math involved. You measure it and you do a fraction and that sort of thing. So some of you are having flashbacks now. I know, it sucks. But the solvent is drawn up that plate and it's drawn through the sample. So as the solvent moves along this plate, the sample is drawn along with it because it is a solvent. So it's grabbing onto that substance and it draws that substance along with the solvent. And it separates out the different compounds in that sample. So different compounds in the sample are going to travel at different rates. They're going to be heavier. They're going to have different attractions to the plates. They're going to have different solubility in the solvents. And because of that, some substances may go really, really far, while some substances may take a lot longer because they're super stuck to that plate, something like that. So it's basically separating out these different things. And based on the chemical, we know how quickly they're going to go, or how far they're going to go in a period of time based on what's in there. So these compounds that are now separated may be colorless, but they can be stained with fluorescent dyes or other specific color reagents that react with the compounds. The travel distance in TLC is a physical characteristic of the compound, and it's one of the ways that these compounds can be identified. So this is like a pretty low-tech way of figuring out what compounds are in these chemicals, just by looking at their physical characteristics. A bit more high-tech is gas chromatography. So it's taking that thin layer chromatography to the next level. So again, gas chromatography is used to separate compounds that can be vaporized. So instead of using a liquid solvent like in TLC, gas is used. Usually it's something like helium or nitrogen. And in this case, the substance is moved along a microscopic layer of liquid or a polymer inside a piece of glass or metal tubing. We call this tubing the column. So you got your column right here, and you inject your unknown sample, you add that gas, it moves it along here. And then the compounds, just like in TLC, they're going to separate out based on that gas and that polymer inside the column. Those compounds are going to interact with the walls of the column, and the different compounds are going to be extracted at different times. So the gas chromatograph computer then is going to have this little detector here at the end, and as these new compounds come through, they're going to be detected by the computer, and it's going to compare the extraction times with the extraction times of other known substances. So that helps you identify what these unknown things are. So based on what you're putting in there, like, oh, this is the extraction time it took, it's going to be this substance. So again, looking at the basic physical properties of this substance. Now we can add on a little bit more to this gas chromatography into something called GCMS. So GCMS stands for gas chromatography mass spectrometry. So this is a method that combines the two techniques, so mass spec and gas chromatography. It uses the gas chromatography portion just like I talked about, same as normal. GS will separate out substances from an unknown sample and use those physical characteristics as it moves along the column to help identify them. The separated compounds, though, aren't just vented out into the air or gotten rid of at that point. They then move into a mass spectrometer. So this actually captures and ionizes the compounds, and this gives them or helps you determine some of their chemical properties. So now you've got some physical properties and some chemical properties of this unknown substance. You put those two things together and you feed it into your computer, and the computer can then identify many, many complex compounds. This is the gold standard for forensic toxicology equipment. So if you end up working in a toxicology lab, this is what you'll likely be using. So these same methods can be used on insect parts in order to figure out what chemicals happen to be in there and at what concentration they happen to be. All right, so we're going to stop there. Up next, I'll talk a little bit more about the entomotoxicology. Let me know if you have any questions.